Hi, everyone. Welcome to today's AP Physics 1 5-able live stream. Today, we're focusing on the gravitational force, especially with its focus on circular motion problems, uniform circular motion problems. So what do we have coming up today? Well, we're going to take a look at some UCM recap. I'm assuming if you've been following along with our series so far, you've already got the basics of circular motion shown in a variety of different ways. We're going to do a little bit on the gravitational force. We talked about this back when we did forces in the previous unit or previous module, but we're going to go back to it again. We're going to play around with a simulation a little bit where we can take a look at the shape of orbits and how gravity and different factors influence that. And then we'll do some free response questions on the topic as well. If at any time you guys have questions, please post them in the chat or use the Ask a Question button. And don't forget to follow 5-able on social media for any and all of your update needs. All right, so a little bit of a recap. Circular motion. Basically, circular motion happens when you have a constant speed, but a changing direction. And because velocity is a vector, we know that there is an acceleration going on there when you change the direction, even if you keep the speed the same. So if we keep the speed the same, we are talking about there being basically an acceleration and a net force. So anytime you've got an acceleration, there must be a net force going along with it, and those will act in the same direction. So here's the if part right here. If we move along at a constant speed around this circle, so the magnitude of the velocity is the same throughout this entire motion, let's say always 10 meters per second, we have an acceleration that will always point towards the center of the circle. Always, always, always in there. Okay. That is where we get the term centripetal force, which means center seeking, and centripetal acceleration. That's what the little c means at the bottom on this equation. This equation is on your reference tables as well. Just remember, little c means center. So if you have centripetal acceleration, it will seek and point towards the center. Okay. And the equation for this is v squared over r. A little bit of a derivation over here. It's the change in v over v, little right triangle trig, in case you're interested in where that comes from. But I'm kind of assuming that you've already covered that chunk of where that delta v over v came from, the v delta over r, all that stuff already was stuff in the past. So just to refresh, we're going to be talking a lot about centripetal acceleration today and Newton's laws in our progress to solve these questions. Right. Uniform circular motion, here's the rest of the stuff here. So we've got an object in a path at a certain radius at a constant speed. Again, constant speed, not constant velocity. The period, capital T, is the time required for the object to travel once around the circle. That means that if we're going in a circle, we have the circumference, which is not spelled correctly. I'll work on fixing that, is 2 pi r, right off your knowledge of geometry and circles. We travel on the outside of it, so our distance we've traveled is 2 pi r, and that gives us our instant velocity, v equals 2 pi r over t. Distance over time, 2 pi r is our distance. Capital T, the period, is our time it takes for that to happen. Now, key idea here. The direction of this motion is always, always, always tangent to the path. As you can see in the image here, the v is tangent to the circle, and down here it's tangent to the circle, and tangent to the circle, and tangent to the circle. That means that if at any point in time we let go of that object or stop putting that force on it to make it go in a circle, that object travels off in a straight line that was tangent to the circle. Okay. As long as we're putting a force on it, we have a force that is a centripetal force. That is the force that points towards the center. Again, centripetal means seeking the center or pointing towards the center. And this is basically Newton's law. There's nothing fancy about the force. It's F equals ma, just like any other force that causes an acceleration. The only difference here is our acceleration is not just a, it's v squared over r, which lets us simplify this a little bit, that the force pointing towards the center must be equal to mv squared over r. Or rephrase, the force causing it to accelerate towards the center must be equal to mv squared over r. This might be a net force, or the difference between tension and gravity if you're talking about spinning something in a vertical circle. On there. All right, next part. Well, let's take a look at going into space then. And this is where we're going to spend most of our time talking about gravity and these objects. So gravity, if you're in space and we're ignoring any sort of drag force because of the atmosphere or anything like that going on, the only force that causes centripetal acceleration is gravity. Gravity, as you might have remembered from previous talks, is equal to big G. G is a constant given to you on your reference tables. Mass of object one, in this case, ME, because we're talking about the Earth, M, little m, the smaller object, over r squared. And this is the key idea here, that gravity is dependent on two masses and the distance between them. So the farther you are away from the objects, the smaller that force of gravity gets, and vice versa. And the bigger the objects are, the stronger the force is going to be. Okay. And that lets us do some cool things like find how fast you have to have a satellite going in order to maintain a given orbit. We're going to spend a lot of time on that in the coming stream. So for right now, we're looking at gravity being MEM over r squared, and we're basically talking about orbiting in a circle. So that being said, let me switch over and we're going to do a little simulation stuff now. For you guys, there is a button at the bottom of this window that should be called FET Gravity and Orbit Simulation. That's the one that I'm using. There's also a link to it in the resources tab for this stream. So either way you want to get there, let me open this up and there we go. All right, so this is something that I basically let my AP kids play around with and just let them kind of discover the relationships on their own. And so really, that's kind of what we're going to do is we're just going to mess around a little bit here. So we have a fairly simple situation. We have a large object, sun, star, large planet, and a smaller planet. And if I just play this through, we can see that, oh, look, the Earth goes around the sun. And we got a nice little timer here to tell us how many days have passed. And we got some things we can change. We can, for example, turn gravity on and off. So if I turn off gravity, what do you think is going to happen? All right, yeah, this is not too hard to understand here. If I turn off gravity, then suddenly we don't orbit anymore and the Earth flies off into space. Now, the key thing here, because we're talking about circular motion, the velocity, as I turn this on, the velocity of the planet, let's turn back gravity on before I reset everything. Reset, turn on gravity. There we go, okay. So the velocity here, we'll put the path on too, is always going to be tangent to the path, tangent to the circle that this object's making. And I know if you're in earth science or whatever, or taking earth science, yes, this is not a perfect circle. It's going to be an ellipse because Kepler's laws and stuff like that. For our sake, we're almost always going to call it a circle. And that's what this simulation is going to have it be as well, is a nice, perfect circle until we screw something else up. And if we mess with something else, we can make it be an ellipse and stuff like that. But for right now, nice circle. And notice that we have the force of gravity pointing towards the center of the circle. This is gravity from the sun pulling on the Earth. This is the gravity from the Earth pulling on the sun. It makes a very nice Newton's second law, Newton's third law, action-reaction pair, where these two forces are equal in magnitude and opposite in direction. And they are nicely perpendicular to our velocity vector right here. And that's what lets our planet go in a nice, simple circle. If it wasn't perpendicular, let's say I suddenly tweak this a little bit, and I may have overdone it here, then we suddenly don't get a circle anymore, but instead we'll have the Earth move around the sun in a much more elliptical fashion. And this is where the speed of the object changes. We are no longer in uniform circular motion because we no longer have a constant speed as we go around this shape. Also, we're not in a circle. But even here, you can kind of see there is some part of this force, the blue arrow, that is pointing towards the center of our circle. or is perpendicular to our velocity. That's why we have it changing direction. If the blue arrow was parallel with the orange arrow, we would just have a straight line linear acceleration. But instead, because we have some component that is perpendicular, we're seeing a change in direction as well. All right. Does that make sense? All right. So if you guys have any questions at any times, please throw up a comment in the chat, and I will do my best to answer it as quickly as possible. All right, so I'm going to go back and I'm going to reset everything here because I can get to our next spot here. So let's just watch this thing go around in one more circle again, just to confirm that we are still actually, in fact, orbiting the sun in this simulation. We haven't broken anything or anything like that in there. So now what we're going to do is we're going to take a look at seeing what happens if I make the Earth bigger. If I make the mass of the Earth suddenly bigger, what do we notice happens? So first thing, this blue arrow got a whole lot bigger. There is a stronger force pulling the Earth and the sun together, or Earth and the star together, because there is more mass, and gravity depends on the mass of the two objects. But what's interesting is that did not change, at least to my eye, anything about the orbit. The Earth is still going around the sun in that circular path we had before. And yeah, not much changed here. We are still looking at the same exact sort of scenario. Well, that would mean that while the Earth's mass changes the force, it does not change anything about our acceleration around. We're still going at the same speed, at the same radius, all the stuff like that. Okay, so Earth's didn't really change very much. Let's see if I can turn this back off. Well, if Earth's mass didn't change anything, what about the star's mass? What if I make the star get bigger? Let's see what happens here. Oh, now we're getting a very different shape to our orbit. And we just settled into another elliptical sort of thing. But the interesting part here is this looks like it's taking a good deal less time to complete. And that velocity vector for the Earth gets ridiculously huge, much bigger than it did before. So that's interesting. So far, if we change the planet's mass, it didn't really change much. But if I change the star's mass, not only did it change the force between them, it also changed very drastically the shape of the orbit and the path that it would follow. We went from a parabola or a circle to some sort of elliptical sort of thing. And then notice if I turn this back down to where it was, we suddenly have our velocity vector being, I don't want to say normal sized, but definitely not as huge as it was before. The vector stays on the screen the whole time instead of having the end shot out somewhere else. So interesting. Somehow our path we take, our orbital radius, depends not on the mass of the Earth at all, or the mass of the planet, but entirely on the mass of the thing that you are orbiting, the mass of the star in this case. On there. Kind of interesting. And then again, we're back to our pretty much perpendicular relationship between the velocity vector and the gravitational vector, which means we're going in relatively uniform circular motion. Okay? Now, just to be clear, this is not anything that we would say to scale. If we wanted to look at a scale sort of thing going on here, this is more like what we'd see. Space is so ridiculously empty that we have so much of these things just not helping our case very much with that. But there's our kind of takeaway here. we can have a planet or a satellite travel in a circle around another object. In fact, let's do the satellite one right here just to show it. Hey, look, we can have a satellite go around the Earth, and it's the same basic concept. We've got a circle going on. Gravity is the force that's pulling towards the center, and the velocity vector is tangent to our path. And again, if I turn off gravity, our satellite goes flying off, never to be seen from again. So yeah, that's kind of the gist of where we're getting at today. So we're going to be combining some Newton's laws, some F equals ma stuff, with this idea of gravity being the force that causes things to move in space, with the idea of moving in a circle. All right. Are there any questions or things you want to see me do with this on here? Because we can do some pretty crazy things, like throw the moon in there, just for example. Oops, with gravity turned on, and then watch the moon travel around the Earth, and there it goes. How exciting! So there's lots of stuff. I would encourage you guys mess around with this, see what happens if you suddenly change the mass of something, and how that impacts other stuff in its orbit. Can you make a stable orbit that makes a very different pattern? Can you make an unstable orbit? Can you make, mess around, see what you can do here, because this to me is really fun and really, oh, there goes the moon. Really a nice tool just to mess around with some of these more abstract concepts and equations in an interesting and easy way. Okay, so the link for this again is in the description. It's in the slides, and it's in that button on the bottom. So if you get a chance, mess around, have some fun. I would love to see what cool things you discover in there. All right. But that being said, let me jump back to our slides here, which is right there. And go. Okay, so basically, this is the gist of what we came up with beforehand. We have gravity, g MEM over r squared. And this, in the orange box right here, is kind of the part that we discovered by accident. Or maybe not by accident. We intentionally did some things and noticed this pattern. That because there's a little m on the force side, and because there's a little m on the acceleration side, those little m's represent the same object, the Earth or the satellite or whatever's orbiting something else. Those drop out. I can divide both sides by m and it disappears. I'm left with this velocity is equal to the square root of gme over r, which means that nowhere in here does the object's mass matter, which is kind of interesting. That it doesn't matter how heavy my satellite is. If I get it up in orbit with a given radius, it needs to have a given speed. And it could be a microsatellite that weighs maybe a kilogram. It could be a communication satellite that weighs 100 kilograms. It could be a space station that weighs several thousand kilograms. Sorry, has a mass of several thousand kilograms. It doesn't really matter. The mass of the object doesn't matter when you put it in orbit. All you have to do is make sure you have the right radius and the right velocity, and it will just go. The trick is getting it up there, of course, and that's why we have NASA and SpaceX and ESA and all the other agencies that do this stuff. But as far as where to orbit, this equation right here, using nothing more than Newton's laws, is all we need to do to say, if I want to have a given velocity, I need to have it at a given radius, and vice versa. All right. So speaking of that, let's do a couple questions. So all of these, see if I can find my page here. All of these questions are in the slides. So if you want to go ahead, or if you're watching this after the fact, don't cheat. Give these a try before we spoil the answers for you. But that's the gist of it here. Okay. So basically, we've got an explorer plans a mission to place a satellite in a circular orbit around Jupiter. Why Jupiter? Because that's what the question is. This could be Earth, Mars, the moon. It doesn't matter. The numbers will be slightly different. So Jupiter has a mass of roughly 1.9 times 10 to the 27th kilograms. Yikes, that's big. And a radius 7.14 times 10 to the 7th meters. Again, yikes, that's big. Just as a note here, and this is hopefully something your teacher has told you and your math teacher as well. But when we're doing these sort of large numbers, just make sure you know how to put numbers in scientific notation into your calculator. On most of them, there's an EE button or an EXP button that does this without having to use carets and parentheses, and generally makes your life a lot easier and less error prone when you have to do math with these ridiculously huge numbers or ridiculously small numbers. All right, so I'm going to switch over to my camera, and then we will go ahead and start solving these questions. New slide. Video. All right, so this is the question. And again, this is also duplicated on the slides. So if you, again, are coming through these after the fact and are wondering where is all this stuff, it's all on the slides that are there. Okay, so let's take a look. So part A really asks us to do just a lot of math. An explorer plans a mission to place a satellite in Jupiter. If the radius of the planned orbit is r, use Newton's laws. Nice, thank you for giving us a starting point to show each of the following: the speed of the satellite and the period of the orbit. All right, so just a reminder here, we're trying to get the satellite in orbit around Jupiter. They told us the orbit is r. Radius, so let's go from the center, is r. I know the mass here is mj, and the mass of our little satellite, let's just call little m for right now. Okay, and we're supposed to show that it's equal to that. All right, so part A, single I, we have, well, sum of all the forces must equal ma. That's my starting point. They said to use Newton's laws, so that's what I'm going to be doing. So I guess the next question is, which forces act on our satellite? How many forces are there of this satellite sitting in space? Well, probably we can definitely say that there is a force of gravity on there, and gravity is going to be pulling our satellite inwards. So there's our force of gravity pulling our satellite inward towards the center of that orbit. And frankly, that's it. There is no friction in space. There's no normal force. We're not sitting on a surface. There's no giant cable pulling us around or anything like that. The question doesn't mention anything about us firing the rockets or anything like that on our satellite. So we don't have a force of a rocket pushing us anywhere. That's it. Okay. So I'm going to go to our reference tables and say that the force of gravity is ma, and the force of gravity is capital G times big M, little m over r squared, and that must equal little m. And now, because we're going in a circle, they definitely mentioned circular orbit in the question. So we will stick with a circular thing here. So this makes mv squared over r. All right. So that being said, let's go through and do a little math for a second here. I want to get rid of the little m's because they don't matter. There's a little m in both my terms. I'm also going to trade out a pair of r's, which is nice and simple here. So this means v is the square root of g times the mass of Jupiter over my radius r. And that's exactly what we were supposed to find in the previous question. So it's nice when they give us the answer and then we just go through and solve it. So big G, mass of Jupiter over r. Part double I says, okay, now we have to find the period. Remember, the period is the time that it takes for this satellite to orbit Jupiter once. So we're looking for a period of a satellite orbiting, and it's got to be equal to 4 pi squared r cubed over gmj. All right. Well, there's quite a good deal of stuff there. Something with pi's and R's and stuff like that that weren't in our case originally. So I guess what I'm going to do to start off with here is I'm just going to assume that I'm copying all this work already, because that's basically my starting point. So I'm going to start at v squared equals g mj over r. So basically, I did f equals ma, g mm over r squared equals mv squared over r, drop some stuff out, and I'm left with this. Okay? Now, the big picture here, though, is v is not in my answer. T is, and T is a time, which means we're going to have to replace V and say that V is 2 pi r, the distance I travel over the period. So that would mean that we've got a velocity squared now. So let's do 4 pi squared r squared over t squared equals g mj over r. All right, this to me looks like a little cross multiplying now, because my goal is to get t by itself. That's what the question's asking us to show. So let's do a little cross multiplying. And we'll get 4 pi squared r cubed. Hey, that's good. We're supposed to have an r cubed in our answer. In fact, everything here looks like it's what we need in our answer, equals g mj t squared. And now we just solve for t. So I'll divide by gmj, and I'll get t equals the square root 4 pi squared r cubed over gmj. And there we go. There's part 2 already done for us. Not so bad. A little bit of algebra. Key idea here was that realizing we had to use both our stuff from part A, forces, circular motion, gravity, and the fact that velocity is distance over time. Put all that stuff together, you get this wonderful thing. This is also, if your teacher mentions this, something like this is Kepler's, wow, my pen is not working. Third law equation. Sometimes we'll run into questions about that. In fact, I'm pretty sure we're going to see that kind of be a common theme throughout the questions that we're dealing with today. When you're talking about gravity and circles and stuff like that, Kepler's third law is one of those that just keeps coming up and up and up. And I'm not saying memorize this, but I am saying you probably should know how you get to this process, whether it's experimental question or other FRQs. Knowing how to get there is a really good skill to have. All right, so there's part B. Sorry, part A is done. Part B, now we want this orbit to be synchronized. We want to make it geostationary, have the same spot over, or be over the same spot of the planet every time through. So they give us a time for that. We have to find the radius in meters. Okay, well, that's not terrible. In this case, we know we've pretty much done all the work. We want to take this concept right here that we just did and solve it for r, and then plug in all the numbers. So I'm just going to kind of grab this and start with it over here, that 4 pi squared r cubed equals g mass of the planet times the period squared. And then let's get r will be the cubed root of g mj t squared over 4 pi squared. All right, well, so g comes off your reference tables. G is 6.67 times 10 to the negative 11th. The mass of Jupiter was 1.9 times 10 to the 27th. The period is 3.55 times 10 to the 4th. And all over 4 pi squared. And then take a cube root of that. So that would be something that I really hope we have a calculator for, because doing that by hand will not be enjoyable at all. But once we get all that stuff plugged in and crunched and numbers happen, we'll get a radius of about 1.59 times 10 to the 8th meters. And again, my advice to you guys for doing this, if your teacher hasn't told you already, find that EE button or the EXP button on a calculator. It's going to make doing stuff like this a whole lot easier. Also, if your calculator, if you don't have a nice handy third or cubed root, you can just remember that a cubed root is the same as raising it to the 1/3 power, and that'll get you the same basic idea. Okay. So far, just to recap, we've done forces, gravity, acceleration in a circle. We solved for the velocity. We've solved for the time, realizing that velocity is 2 pi r over t. And now finally, we've gone through and taken that same step, solved it for r this time, plugged in a bunch of numbers, and got an answer out for that. Okay, next part. Part C. Now, suppose the injection of the satellite in the orbit is less than perfect. For velocity differs, sketch a resulting orbit. J is the center, the dashed circle is the desired orbit, and P is where we entered. Also describe it qualitatively but specifically. Okay, I can see this being one of those qualitative, quantitative questions. This question itself is from 01, so it was never on an AP1 exam, but it was on an APB exam. So something like this where it's qualitatively but specifically, this is one where it'd be nice to be able to describe that sort of thing. Okay, so when the satellite is at the desired altitude, its velocity is the correct direction, which is good. So our velocity right here is pointing sideways, which it should be, but its speed is slightly faster than the correct speed for a circular orbit of that radius. Okay, well, if we go back through, I'm just gonna look at this now, stealing from up here, velocity depends on G, M, J, and R. So if V is bigger than it should have been, that means, if this fraction gets bigger, V gets bigger. So we can't change G, we can't change any of that stuff. But we know we do have to hit at point P. The problem here is we are going a bit too fast. Going too fast means we tend to overshoot our orbit a little bit. And if you're wondering, we can go check that out on our gravity simulation and just verify that that's what's going to happen. So I'm going to jump back to the same gravity orbit sim we were playing with before. There it is right there. Let's reset it. Okay, so right now we've got our velocity in place, and I'm going to make it bigger than it should have been. And that might be too big, but let's take a look at what shape the path makes here. Zoom out, zoom out. I made it too big. Oh no. Let's try just slightly bigger. Okay, so hopefully we will see this thing travel in, there we go, a much more elliptical path. And notice that it is getting ridiculously far away from the object it's orbiting. In the question's case, it's Jupiter. In this case, it's a star. But notice how stretched out that ellipse becomes. That we're looking at something very elliptical going on here because we increased our velocity. It was too big for the desired orbit, so we made it a much wider, a much more elliptical orbit. Now, the math for this part, we really can't do a ton with until we talk about angular momentum. Angular momentum is typically a topic that is not going to be covered until, for my students, February, March timeframe. Your teacher may teach things in a slightly different order, but basically there's a equation and concept that explains this. We just don't know it yet. So for right now, we're just going to kind of say that it is squished out a lot and much longer than it should have been. Okay. And the last question with that part says, now we're at the same altitude, but now we're going slower than we should have. So let's crunch that down a little bit. Let's go to slower speed. What happens here? Well, it's pretty much exactly the opposite of the thing that happens in the too fast scenario. So too fast, we get stretched out and we get an ellipse. Here we get an ellipse, but it's scrunched down a lot as we go around there. Okay. And these are the shapes that you would draw in. Every single one of these will include the injection point. It includes point P, the point we started at right over here. But it will just be the shape is slightly different. And again, if you want the math going on, if you're interested, we can go into it right now. Basically, it's a momentum question, but that typically gets covered after we do spinning things and rotating things in a much broader context than just circles and gravity. So hold on to that. We'll definitely come back to this question again later on in the year and address why these shapes occur. All right. Any questions so far? All right. So that was the kind of derivation question. Pretty common to see those, or that style question on an AP. I don't think we've had an AP1 exam so far that has done derivations of planetary motion and stuff like that, but who knows? This year might be the lucky year. All right, so I'm going to move ahead then and do the next question. Again, this is in the slides. So if you're interested in watching this later, thanks for watching this later. You can go ahead and work through these with us. All right, so this one is definitely an experimental question. Not so much an experimental design question, but a experimental interpretation question on here. We're given some data. Some astronomer took some data for the moons of Saturn, and we want to use it to figure out the mass of Saturn. This is super cool because this same concept, not with Saturn, obviously, but with other objects, is used to help us determine the mass of planets, the mass of stars, that sort of thing outside our solar system. So all the exoplanets and stuff like that that we have discovered, again, planets outside our solar system that we can talk about their mass and their orbital radius and their orbital period and stuff like that. That lets us do a ton of assumptions about it. Maybe not assumptions, not the right word. Learn a ton of things about it based on just doing this very simple, maybe not simple, doing this process through it. Okay. So A and B, here we've got all this experimental data. We want to write an algebraic expression for the force of gravity between Saturn and one of its moons. All right, so this one hopefully is nice, easy, free points. I would love to get that question on an AP exam for points because really all it is, hey, can you write down the force of gravity equation and can you plug in the mass of Saturn for one of the masses and I'm just going to leave it as an M, mass of the moon over capital R squared. And that's it. That right there gets you some nice, easy, free points. Probably only one, but hey, it's a free point. So pretty awesome. Part B gets a little more complicated. Use your expression from part A and the fact that we're assuming circular orbits to derive the orbital period of the moon as a function of its orbital radius r. Okay, this part right here, again, is another Kepler's third law problem. Go ahead and derive it. That's exactly what they're asking us to do here. So, again, we're going to start off assuming circular orbits. We're going to start off with Newton's laws. F equals ma. Force of gravity is mv squared over r because we're assuming it's a circle. And again, we also know v equals 2 pi r over t. That's where we get the t part coming from. So g, mass of Saturn, mass of our moon, over r squared equals moon. I'm going to leave it as a v right now. We'll simplify it in a second here. All right, we got that. A little m on both sides can disappear. r on both sides can disappear. And then we'll get g mass of Saturn over r equals 2 pi r over t squared. So I'll plug in that v term right into there. And then square everything, cross multiply. T squared times g times the mass of Saturn is 4 pi squared r cubed. Again, exactly the same spot we were beforehand. Just again, knowing how to do this, don't memorize it, but know how to get there, going to be useful for you. And I'm just going to solve it for t because that's what the question asks us to do. So the orbital period t of the moon is a function of its radius. So yeah, t squared equals 4 pi squared r cubed over g ms. And you're probably good leaving it here. Although if you really wanted to, we can get t equals just square root it. And there we go. There's part B. Again, some algebra, and that's really about it. Going through and crunching out part B. All right. Questions on the derivation? I know I went through that one quickly. Okay. Then, now we get to the actual explanation part here. I've got all this data. What do I have to graph in order to turn this wonderful, messy equation into something that gets plotted as a straight line? And I want to use it to figure out the mass of Saturn. Oops. And there goes my camera. Well, that's wonderful. That's not good at all. Okay, well, we're going to, I guess, good news is we are pretty close to being able to switch over here. This is where I would do it if you had a calculator or something like that. I do it on a spreadsheet because that's my backup plan right now. So I have this stuff put in here, and they give you 2 columns up at the top of the question to derive your stuff. Well, wonderful. What can I use to make that derivation work? And the question here is simply, I have this wonderful equation, t squared. Let's type in the right thing here. So I know t squared equals 4 pi squared r cubed over g m. And again, I apologize. This is not the best way to represent this information, but I don't have a camera right now. So let me try to get this camera up and going again. Hopefully we'll have better success with this. But basically, what we're going to do is we're going to turn this equation into y equals mx plus b. Saying that, let's see, are we back up and running? We got a badink. Here. My phone's trying to tell me something. Okay. So that was not what I needed, but we'll just see if this comes back up. Anyway, basically, we're gonna apply y equals mx plus b to that nasty, wonderful equation on there. In this case, we're going to say that t or t squared, either one could work for this. And then our x value is going to be either the radius cubed or the square root of the radius cubed. Personally, I am a big fan of the radius cubed because if I don't have to square root something, I don't want to. So I think I'm back with this camera. Hey, there we go. Okay. So my apologies for that. The basic idea here is that we are going to take this line right here, and I'm going to put t squared on the y-axis, and then r cubed on the x-axis. And what this should do is basically anything in my equation over here that was not a t squared or an r cubed becomes the slope. So the slope in this case, this 4 pi squared over g ms is the slope of that graph. Now, it doesn't have to be this one. Like I mentioned, you could have done the square root of t, or t and the square root of r cubed. Then your slope would be the square root of all this stuff. But I don't want to square root stuff if I don't have to. So that being said, let me grab my spreadsheet. I'm going to start plugging stuff in here. So I want t squared, and I want r cubed. And this is basically what they're going to want you to do on the data table that's on the question. I can't edit that, so we're just going to work with it here. Plus, doing stuff in Sheets or Excel makes our lives a little bit easier. So I want the period squared, and I want the radius cubed, and we're getting gigunda big numbers, which is okay. And we put them down, and there's our stuff. And now we got to graph it. So again, I'm graphing it on here. The question has us graph it in the provided axes, but just for the sake of showing, I don't want a column chart. I want a scatter chart. And my x-axis is going to be this one. All right, and hey, that looks reasonably linear. Okay, let me go ahead and throw a trend line on here so we can take a look at that, because the last part of this, thank you, Google. The last part of this is to basically get an equation for this. And in my case, the equation for this graph is roughly 1 times 10 to the negative 15th. Okay. The cool part is then if I take that 1 times 10 to the negative 15th, I can then go through, plug that 1.05. I'll just jot this down. Plug that back into what I know my slope has to be, and then we can solve for the slope. And that is that. How would I get the camera up? Yeah. Okay. So we're given this 1.05 times 10 to the negative 15th is my slope. We know the slope needs to equal 4 pi squared over g times the mass of Saturn. This will equal 4 pi squared over g mass of Saturn. So I'll take this, I'll multiply it and do some division here. Basically, 4 pi squared over g times 1.05 times 10 to the negative 15th equals the mass of Saturn. And if we go ahead and just stick numbers to that, the mass of Saturn is approximately 5.64 times 10 to the 26 kilograms. Okay. So again, I pulled G off the reference table, 6.67 times 10 to the negative 11th, and we end up with that one pretty much plugged in as is. All right. Hopefully that was helpful and useful. All right, and I think we've got time for one more. So I pull this one on. This is 95 M3. Again, older question, more just practicing the mathematics and the process there of solving these. Okay, so this one, oh, by the way, part D is crossed out here because that involves angular momentum. That's the concept that we'll get to later on in the course, but not right now. So it's there. It was part of this question originally on the AP, but we're just going to ignore for right now because, well, we can't do it yet. So really, we have an A, B, and C. We want to find the acceleration of star A, where you have two stars, A and B, orbiting about a fixed center of mass. Okay, so A, you can imagine that there's a really heavy thing right here. Radius A, radius B, and we want to figure out expressions for these in terms of RA, RB, T, and some known constants, capital G being the big one, I'm going to guess. Okay, so I want to find the acceleration of star A. Well, I can do acceleration two different ways. I can do acceleration with AC equals v squared over r, because that's one way to do it. Or I can do it with sum of the forces equals MAC. And looking at what I have to do here, the fact that they're asking us to find the mass of B and the mass of A as later parts of this question tells me that, yes, while I could do F equals MA, that is probably not the best way to do this question. They also didn't mention anything in the question about masses or forces or stuff like that. So I'm going to start with AC equals V squared over R. So AC, that's what I'm looking for. V for star A has to be the diameter or radius of the circumference of the circle times the time it takes to go around, which is t. So my velocity is 2 pi r a, because it's the radius of A, over the period quantity squared all over RA, where RA is the radius of the circle we're orbiting around. Okay. We can then crunch through some numbers. For pi squared RA squared over T squared over RA, and then fraction over fraction, copy, change, flip, or however you have learned it. Basically, it boils down to this one cancels out one of the squares. And we're left with that our acceleration is 4 pi squared RA over T squared. All right. Questions on that one? All right, so there's part A. Part B says to find the mass of star B. Okay, so I want to find the mass of star B. What can I do here? We don't know the acceleration of B. We don't know the force. Oh, but we could figure out the force. We could figure out that all the forces must equal a mass times an acceleration. That has to be true for either star A or star B. They're both orbiting in circles, so this equation holds true for both of them. The force here is the force of gravity. And that is capital G, the mass of A, the mass of B, over the radius. The radius here between A and B must be RA plus RB squared, because in the gravity side of things, radius is from the centers of the objects, not necessarily the center of the circle. On the acceleration side, this R is to the center of the circle. Kind of wish they had a different symbol for it, but just got to keep that in mind. All right, so we've got that put in. Now this must equal, oh, you know what? If we put in the mass of A in this side, and we know the acceleration already, 4 pi squared RA over T squared, then the mass of A will just cancel out because it shows up on both sides. So if we treat it as star A is orbiting star B, then we can say the mass of A doesn't matter at all. And we can go through and basically work this out, solving for MB. And you know what? I'm not even going to bother expanding things. I'm just going to take and multiply this over to the other side and divide by G. And say the mass of star B must be equal to 4 pi squared RA times RA plus RB squared all over T squared times G. And there's the mass of star B found for us. All right, that wasn't too terrible, although I guess if we didn't realize that this acceleration, that we had to use our answer in part A, in part B, this could have gotten a little bit more out of hand. But I guess that works. So now, where do we go from here? Part C says to find the mass of star A, which kind of makes me think, are we just really repeating part A and part B again, but for the other star? And I think that's kind of where we're going with this. There might be a shortcut, but I'm kind of tempted just to run through it and just say, okay, I'm going to just do the AC equals V squared over R. This is 2 pi RB over T squared over RB. So the acceleration is 4 pi squared RB over T squared. Again, same exact work that I did in part A. And then sum of the forces equals MAC, GMA, MB over RA plus RB squared equals 4 pi squared RB over T squared, all times the mass of B. MB's cancel. And wow, do I really do all that work when I could have just, okay. Well, so there was a shortcut. All it was, and I can't believe I didn't see this earlier. Hopefully you guys did. Hopefully you're yelling at me through your computer saying, hey, that all we did is we changed an A for a B and a B for an A. And that was the only change we had to make in there. And not like the math was difficult, but we did it twice without realizing it. So, bleh. Well, there's a good lesson. A lot of times there could be a shortcut. But anyway, that is 95M3. And again, part D is there. We'll cover part D later on in the year, just because. All right. So that brings us pretty much to the end of the stream. Thank you guys for joining me, and I hope to see you guys next time for the next AP Physics stream. I think we're continuing with circular motion and getting into energy potential kinetic transitions that way. So have a great night, and thank you very much.